part of buffer overflow. So buffer overflow, the extra data you're putting in can have many different purposes. It can be totally innocent, where it's just, oops, I didn't mean to do that. Sorry, I overwrote something. Or it can be, oh, I totally meant to overwrite something and infuse malicious software into your memory, kind of thing. Or programs. Even, I mean, when you're storing things in memory, they can be actually executables that run. So, got to be careful as to what that all is. Okay. So, my very sad drawing. Okay. So there are two examples of, and let me just escape for now. Oops. Discard them. Okay. And I just wanted to go to my notes for this part. So there are two, I mean, there are more than examples of buffer overflow, but one is the Morris worm. And most of you weren't even born in 1988 when this one happened. And that was the idea where there was buffer overflow in basically that caused almost a complete shutdown of the internet. And then the other one, which is a little maybe more relevant, is apparently in The Legend of Zelda, which I am not a gamer, so I can't even speak to that. The horse's default name was Epona. Am I pronouncing that? Or is there anybody who are Legends of Zelda experts?
Do you remember which game it was? Like
it's
what
Twilight
console?
Princess.
Oh, okay. Yeah, I never played that one.
Okay. So the horse's name was Epona, Epona. So 1, 2, 3, 4, 5 letters. But to kind of make it more fun, when they developed the game, they allowed you to choose the horse's name. So the default name just means that's the name. And if you don't want to change it, that's the horse's name. But you were allowed to choose whatever you wanted. And so, of course, you're talking about gamers who love to like try to break things. No offense. I have many gamers in my house, but who are smart and like to say, like, yeah, let's see what I can do here. They're letting me put in the horse's name. And they put in string names that were so huge that they basically brought the game down. So now there are, so what can you do? If you want to let someone put in the name of the horse as part of the fun part of the game, what can you do that would prevent what happened from happening?
You could validate the input and not allow them to input anything over 5 or whatever.
Yeah, you can kind of check string lengths, and you can say, no, nothing over 5, or maybe we'll give you 10, or we'll give you 30. But certainly, before you start trying to write something to memory, you should be checking you're doing input validation, which is something we'll talk more about next week in our remote lesson. So tonight, what we're going to show is that Java and C, and I'll kind of use both, behave very differently. And one is much more vulnerable than the other. Okay. So we're going to talk about heaps and stacks. We're not going to get too heavily into them, but the idea is that everybody took data structures, so stacks and heaps are something we're familiar with. And when we allocate objects in Java, we just kind of reference them. So when we do this line of code here, the class C, where this is out. Okay, so let's say what class C equals new class. What is that line of code doing, you guys? Highlight. What is this line of code doing? Not in terms of memory, just in terms of Java.
Aren't you creating an instance of that class?
You are. You're creating an instance of that class, and you're naming it. You're turning it basically into an object, and you're naming it C, the letter C. Well, not to be confused with C++. Probably a bad example. That means that the class exists, but we're going to just point to it, and we're going to use C sort of as this reference variable to point to it. So there is not truly memory allocated. You're turning the class into an object, an instance of the object, but an instance doesn't mean that it exists. It means it can be referred to. Whereas in C++, when you create objects in C++, they take up these blocks of memory. And when these objects are created, there is space and memory allocated for them. Okay? So you create more objects, more space, more space, more space. So it's a little different. And that's important. And we'll draw some pictures. So in C, or C++, one and the same, as we start storing things in memory, our stack keeps putting things, oops, let me just change it to, so as we put things in a stack, do we go top down or bottom up? Okay, so this part is the stack memory here, the stack memory. If I put, say I want to store the letter A on a stack, does it go here? We think of like stack as memory positions? Or does it go here? So do we put it at the bottom or do we put it at the top? That's really the question. Does it go to the top or the bottom when you're putting something on the stack? What's the operations on a stack, you guys? What are the actual stack operations?
Push
We
and
both start
pop.
with the letter P. Yep, pushing and popping. So when we push something on a stack, it means that we put it on the very top. So the most recent item put on the stack gets put on the very top. So if we take, like, sort of draw my own little picture of a stack. So I kind of just say, oh, here's my little stack example. Right. So say in my stack, I have some memory. And so I want to first store the letter A. Okay. So that's the top of the stack, right? There's on the top. But what happens now if I want to store the letter B as well? I now want to push B. I want to push B on the stack. What do I have to do in this drawing? Does B just come here?
Will it push A down and then B now goes on the top?
That's exactly right. When you are pushing onto a stack, it's like a Pez dispenser. That's my best sort of definition for a graphic of it. When you push onto a stack, then if I'm going to put B on, A will get pushed down here.
Last in, first out.
That is last in, first out, right? The last one in is the first one out. I always use the Pez dispenser as an example. Okay. So I'm going to keep going on my merry way and I'm going to say, oh, now I want to put, I'm not going to do alphabetical. So now I'm going to, and sorry, it's not easy to push to erase in. So now I'd like to put, let me just draw this line. So just maybe a stack of just 3 spots. I'd like to, I don't know, put the letter J on it. Okay. How is this, now I'm going to push the letter J on. How's this diagram of my stack going to change? Am I going to put J down here where I'm pointing?
No.
No. Where's J going to go? Or what's going to look different?
It should be JBA.
JBA, right? So A is going to get moved down, B is going to get moved down, and J is going to get pushed on. So now I'm going to have the A got pushed down, the B got pushed down, and now the J is there. Okay, thank you. I just pushed my J. But now if we're kind of looking at this diagram here, we're saying this is like my diagram of the stack. So I'm kind of just referencing this here. This refers to this. And now I've come along and said, oh, you know what? I now also want to push, let me just cross you out. I'd like to push the letter R. This is the top of my stack. This is the bottom of my stack. In C, it is not going to stop me from putting that R on, even though the stack is full. What's going to happen? What do you think is going to happen when I try to push R onto the stack?
It's going to get pushed onto the heap.
What's going to get pushed into the heap?
Probably A, right? Yeah.
Yep. So what would happen is, and let me change the color so I can like literally write it. Right. So I have, here's my, oh, purple does not show up. Let me try the contrasting color. This blue. Here's my heap hanging out underneath. And so what's going to happen when I try to push the R? The following. My A and just finish writing you. And I will change my colors. My A is going to be come into the heap. My B will now be at the bottom of the stack. The J will be here, and that will allow me to push the R. So all of a sudden now, memory that I was really should not have been able to overwrite or to go into in the heap allows me to go in. Because when we load a stack loads down. And the weird part is if we start allocating memory in the heap grows up. So we have this sort of push-pull idea where as our stack grows, we start invading the heap space. And as our heap grows, we start invading our stack space. So really, as our stack overflows, we start writing into memory spots in the heap. And if our heap, the way the memory is allocated, and certainly I'm not going to get into the algorithms for how heap access versus stack access, what goes where, because there's very definitive sort of definitions in the architecture of a computer, what goes where. But as my heap grows, it's going to overflow on the stack. As my stack grows, it's going to overflow in my heap. And that's what we're showing. The heap is the blue. And the stack was all in yellow. And they're going to basically just invade each other's space, overflow into each other's space. Okay, great. And if we overflow enough, we might actually start coming into more, like we should not be able to get to permanent storage. It should just be the dynamic memory. What do I mean by dynamic memory? Does anybody know what that is? What dynamic memory is? What's the difference between something that's dynamic and something that's static?
Is it dynamic always changing? Whereas the static is
right? Dynamic memory is memory that's changing, and it can change on the fly. Something that's static, not the Java definition of static per se, but something that's static is fixed. Also, a dynamic person is very, changes all the time. A static person is more like stays in one place kind of thing. So this is dynamic memory, should be changing all the time. Because it's changing all the time, we're very vulnerable to the idea that it could possibly, do what I'm saying, which is override each other. All right. Any questions about that? Like how that diagram, how the stack could invade, sort of overflow into the heap space, and the heap memory could overflow into the stack space.
So I have a question. When you're overflowing if the heap gets full and it goes back to the stack, does it overwrite it?
Yeah.
Okay.
Yeah, you know what? That's actually what I should have shown, was that there was good stuff in the heap that we overwrote. Maybe there was something really important in the heap, and all of a sudden, because we were pushing too much on the stack, we overwrote that, or vice versa. As the heap is filling up and up, there's important information in memory in the stack that the heap will overwrite. So that's a really good point. Right. So this class is all about software security, so we can draw all the diagrams we want, but we always have to talk about preventative measures. And so Michael Spadaro was saying one of them is to make sure in the code that you do not take more information in or try to store more information than you have room for. Sometimes you just don't know that. And then the other way to really make sure you can limit your buffers. You can certainly make fixed amounts and be very mindful of limiting it. And the other thing is, and I can't stress enough the importance of testing. Okay. If you say the people who did Legends of Zelda game, right? We'll go back to that. And so when they were testing it, and the horse's name, the horse's default name was Epona. Okay, probably pronouncing that wrong, but whatever. So my guess is they probably didn't test it for a whole lot. Maybe they tested it for, maybe a couple other names with maybe 4, 5, 6 more characters. But at the end of the day, they did not test it for like 150 or 2,000 character name to see what happened. Because if they had, they would have figured out that was a problem. So testing is really important. I think students don't do that. And I find I started doing it more when I was working professionally, especially my first job was working on an aircraft. So you really want to make sure like people's lives depended on my software or the software my team was developing working. I guess it's a little different, when you're doing financial, when I worked for the bank, it was important because people's money depended on it. But my very first job had to do with people's lives. And so our testing protocols were so rigid to make sure that like no scenario was not covered by our testing. Now, obviously the unavailability of the crashing of the Legends of Zelda game is not the end of the world. But my guess is the software developers took it a little lightly, and they did not test these like worst case scenarios. And testing software's worst case scenarios, if you pick anything away from this course, that's what you've got to think of. What's the worst possible thing that could happen? Let's try that and see if our software can be broken. It is sort of a glass half empty, and it's a negative way of approaching, but that's what you have to do in software security. Test the worst case scenario. It's easy to test all the ones that are going to work. That's really easy. So just to clarify more stacks and heaps, a stack is like a Pez dispenser. A heap is more like a tree. It kind of grows and they grow in different directions. So I like my little pictures. More definition, someone said, I think Matthew said stacks are LIFO, which means the last, if you're visual, the last book in will be the first book out, and you push and pop on stacks. And so as you're you're pushing this book, if there's no room in the stack, may get pushed onto like the heap, if we want to kind of follow along that sort of theme. Right? And here's an example of a program stack, and you will notice that there really is just 4 characters allocated. So if I try to store, we'll see in certain languages, more than 4 characters, I all of a sudden will be overflowing. Because if I try to write another character, I will start. This is my overflow area. Oops, that's weird. I like the red better. This will be my overflow area. So if I try to put in, say I want to add TUV, it's not going to just happen this way, right? It's not going to just tag on at the beginning. Instead, I only have 4 characters allocated in my stuff variable. So I will have the V and the W and the X and the Y, and then what's going to happen to the Z?
It'll move to overflow, right?
Yeah, it's going to move here. Right. going to move here. And so if that 0 had some importance, or whatever was in that memory position had some importance, it's gone. You know, if that was something like, if that was the, I don't know, something like the PIN number, one of the numbers in a PIN number for your bank account, yeah, you know, to make sure that it matches when you input your PIN, it's gone. Mm-hmm. It's gone. Mm-hmm. You can play with some of these visualizations. I just gave you the links. You can kind of play with stack visualizations and heap visualizations as you'd like. Same thing with heap. A heap is an area of memory that is out, like we said, is dynamic, meaning it's allocated on an as-need basis. But as a result, we can overwrite into a heap because it's dynamic. It's growing and shrinking as the program, or as a program is running. And you guys should hopefully also saw heaps in data structures. This is not going to be a heap lesson, but when you store information, there's kind of two ways to visualize it on a heap, sort of as like a binary tree. And then that basically translates into what people are more comfortable looking at as an array. But this is one and the same, right? The 1 is in the 0 position, 3 is in the first position or index, 6 is in the second, 5, then 9, then 8, then -2. So it's just the idea that you can visualize a heap as a binary tree. This is not a balanced binary tree. Well, it's sort of balanced as far as nodes go, but not numerically. And and heaps come in min first or max first. But this is in first heap. This -2 should have moved up there, but apparently it overflowed and it was not able to do that. Right? So whichever way you want to visualize a heap, if it makes it easier for you to visualize it looking more like a stack, that's great, because here's your stack diagram. But most of the time when you learn it in a class, you kind of learn it as a tree structure. And so if all these little nodes contain data, the idea once again is that if I'm out of room on my heap, I may have to go into my stack to save it. This is something you can just read at your leisure, difference between stacks and heaps and all. And there's examples here for, here's like an example. It's sort of done for you where your stack is going to contain your name and a return address. And now the evil code came in. And what did the evil code do in words? And take a second to look at it, just kind of explain, can someone explain to me what this diagram is saying or telling you?
What I guess what did it overflow into the return address?
It did. And as a result, you don't have return address now is an evil address. So where you were supposed to return to when whatever this code was executed, now you're not going to pop back to like the good place where you were supposed to go. It's going to send you somewhere else. It's like misinformation. It's saying, oh no, that's not the right house. No, not there. You go over there instead. And there's the evil witch in the house instead. So because it was able to overflow, they put in their name, and their name not only contained God knows what, but also they were aware of like how many characters were allocated for the name, and they put in more than that. And then they made sure, that's the other thing, a purposeful malicious buffer overflow attack is actually calculated. They figure out exactly how many characters of good stuff to put in before you start putting in the bad stuff. Right? So it's very, very calculated. It's not just randomly, let me put in 100 characters and see what happens. Purposeful bad characters are put in. We're going to try to recreate that ourselves tonight and all. Right? So they decided whatever is here, it was very purposeful. You say we wanted everything to go to address 1, 2, 3. but the evil code they want executed is at 456. So they made sure when they overflowed, when they put in more characters than there's space for the name, that they put in 456. That this is the address of where to take you, where is quote unquote they're calling the evil address, which I love it. I probably should have made it red because it's the evil address. So once again, how could this have been prevented?
You put a stop somewhere, or put some kind of limitation on it?
Yeah, I mean, a stop, I can put an if statement. And so what am I going to look at that's going to sort of raise that stop? Sort of like say, whoa. So what sort of like that's going to trigger that stop or which stop meaning that it's not going to actually store the name or the information input in memory.
So when you write the code, well, I guess you are putting a limit on the code on the name size, but it's overflowing that. So I guess you put that stop statement in there, and if it's greater than whatever that number is, to do something else or to stop it or reject it or something.
I love it. Yep. In real general terms, that's perfect. You're going to look at that whatever values put in, and if it's legit within the number of memory allocation that you have, that's great. And if it's not, then you're like, no, don't do this, and stop or set an alarm or throw an error. You could use try catch depending on what language you're in. You could do an exception handler. So there's all kinds of different ways to handle it. But the key is to look at how many characters are expected here, or what's the amount of memory allocated for here. And once you start exceeding that, then you've got to put checks and balances in place in your code to make sure that doesn't happen. And just an aside, just go to here. For example, let's just see. I got a nice little time. There you go. So, for example, when you are, creating primitive types in Java, it's very clear how much memory size you have for, like, say, an integer. So if you allow a user to input an integer and you make the variable a data type int, and they go ahead and they put in some value that is, larger than these values, if you want to talk about numeric, maybe a little easier, a byte. Let's just talk about a byte. If I allocate something to be a byte of data and I put in a value 125, do I have buffer overflow?
Yes.
For 125?
I'm thinking about 1024. I think it's 1024 is 1 byte. Yeah, if it's 125, you should be good.
Okay, so
Because it goes between
125.
the 128 and the 127, right? That's there to describe.
Right. So I have sort of like for an 8-bit sign value, I have my lovely. So as a byte, I have 1, 2, 3, 4, 5, 6, 7, 8. And so as long as I, right, and so if it was 1111, I believe it's like 255. I guess 1 is a sign bit. That's why we're going plus and minus 127, 128. So I won't go too crazy binary to decimal, but I have these basically 8 bits set up. Each one of these is a bit. It's a 1 byte. And so if I put 125, I'm going to be able to represent that. And I can't help myself. I love binary numbers. The 2 to the 0, or I'll just do it this way. I'll probably pick the number that was probably. So this represents 1, 2, 4. This represents 8, 16, 32, 64. And we're going to